Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like efficient OpenMP programming, program profiling, performance pitfalls. Let's get started. Slide 1. Efficient Open Programming, Basics and Goals. Let's start with understanding what efficient open programming means. When we use open for parallel programming, our main goal is not just to make code run in parallel but to run it efficiently, that is, maximize speed up while minimizing system resource usage. Parallelism should save time, not add overhead. First, efficient open programming means writing code that takes full advantage of multiple cores without unnecessary work. Code optimization in Open is important because poorly written parallel code can be slower than a sequential one. We should avoid creating too many threads. Remember, creating and managing threads also takes time and system resources. Synchronization should be minimized. If threads keep waiting on each other due to synchronization, the advantage of parallelism is lost. Loops are most common in computation, so focusing on loop-based parallelism is critical, but we must divide loops properly. Avoid false sharing. This happens when threads write to adjacent variables stored in the same cache line, which causes unnecessary communication delays between cores. Static scheduling works well when each part of the loop takes similar time, but for tasks that vary in workload, dynamic scheduling is more efficient. A simple example, if we are adding elements of an array using threads, we should divide the array equally to avoid one thread doing more work than others. Slide 2. Program profiling in Open. Profiling is like checking under the hood of your car to see which part is slowing it down. In programming, profiling analyzes code performance. Profiling helps us find bottlenecks, which are parts of code that take the longest time or use too many resources. Tools like gprof, Intel vTune, or simple tools like NuTime allow us to analyze open programs to know where performance drops. Profiling helps monitor CPU usage, memory usage, and how threads are behaving. For example, we might see that some threads are always busy while others sit idle, a load imbalance problem. Profiling also highlights excessive synchronization, like too many barriers that force threads to wait unnecessarily. An example, suppose we are multiplying two matrices in parallel, but profiling shows some threads finish early and others take longer, indicating improper workload distribution. By profiling, we can optimize loops, balance load, and remove unnecessary synchronization to make parallel code actually fast. Without profiling, we might think our code is efficient just because it's parallel, but it might not be. Slide 3. Performance pitfalls in open programming. Even though open makes parallel programming easy, common mistakes, known as performance pitfalls, can make our parallel code inefficient. First, creating too many threads is a common issue. For example, on a machine with 8 cores, using 100 threads will make the system slower due to overhead. Improper data sharing. If threads access and modify the same data without proper synchronization, data races occur, leading to incorrect results. False sharing is when multiple threads modify different variables but located in the same cache line, causing slowdowns. Excessive synchronization, such as unnecessary use of pragma omp critical or barriers, makes threads wait when they shouldn't need to. Load imbalance, when threads don't get equal amounts of work, so some are idle while others are overloaded. Not enough parallelism. If we try to parallelize very small tasks, the overhead of managing threads may be higher than the work done. Ignoring hardware limits. If the system has 8 cores but we use 16 threads, threads will compete for resources, reducing efficiency. Ignoring data locality. If threads access data scattered in memory, it leads to cache misses, slowing execution. Parallelizing small loops. Very small loops don't benefit from parallelism because thread setup time is larger than the loop execution time. Slide 4. Tips for writing efficient open code. To avoid those pitfalls and write efficient open code, here are some important tips. Keep parallel regions large and meaningful. Instead of creating many small parallel regions, define one large block where parallelism is really needed. Use private variables for thread-specific data to avoid data races. If a variable is used inside a loop and doesn't need to be shared, make it private. Use reductions for operations like sum, product, or min, max that combine values from multiple threads. It automatically manages synchronization. Minimize critical and atomic sections because they make threads wait for each other, reducing parallelism benefits. Choose the right loop scheduling policy. Static works for equal workloads. Dynamic or guided helps when tasks vary in size. Avoid nested parallelism unless really needed, because creating threads inside threads is very costly. Ensure data locality. Make sure threads work on data stored close together in memory to avoid cache misses. Avoid redundant work inside loops. The loop body should only contain work that must be done repeatedly. Example: if we want to sum array elements, divide the array into equal-sized chunks and assign each chunk to a thread using pragma omp parallel for reduction, plus sum. Slide 5. Advantages and disadvantages of Open. Advantages: easy to implement. Open adds simple compiler directives to existing code. Reduces development time, faster than writing low-level thread management code. Incremental parallelism: we can parallelize one part at a time and check performance. Well supported on multi-core CPUs, used widely in industry and research. Built-in synchronization constructs, makes it easier to manage shared data. Flexible loop scheduling for dividing work efficiently. Portable, works on different systems without major code changes. Efficient for loops, Open is great for scientific tasks with many loop iterations. Supports tasks, useful for irregular or complex parallel workloads. Disadvantages: limited to shared memory systems, not usable for distributed clusters. Performance suffers if not used properly, needs careful optimization. Debugging parallel errors like data races is harder than in sequential code. Poor scalability beyond a certain number of threads, shared memory bottleneck. Requires tuning to balance load. Synchronization overhead if not used wisely. False sharing risks if data not aligned properly. Not suitable for all problems, especially if they require huge distributed memory. Performance depends on hardware, so tuning may vary on different machines. Slide 6. Differences between efficient and inefficient open code. Here, let's talk about how efficient open code differs from inefficient code. Efficient code divides work evenly among threads. Inefficient code leaves some threads idle. Efficient code minimizes synchronization, using it only when necessary. Inefficient code overuses synchronization like barriers. Efficient code uses correct data scoping, avoiding shared data races. Inefficient code improperly shares variables, leading to errors. Efficient code uses proper scheduling, like dynamic scheduling for variable tasks. Inefficient code uses defaults even when tasks vary. Efficient code keeps parallel regions broad and meaningful. Inefficient code has too many small parallel regions. Efficient code avoids false sharing, aligning variables to avoid cache line issues. Inefficient code doesn't care for memory layout. Efficient code uses data locality, keeping data near threads for faster access. Inefficient code causes cache misses. Efficient code avoids parallelizing small loops, focusing on substantial computations. Inefficient code parallelizes even trivial loops, wasting time. Efficient code uses profiling to optimize, while inefficient code is unprofiled and unoptimized.